Welcome to the Australian Water School, the home of demand-driven industry design training for the global water sector.
Welcome. The Australian Water School today celebrates its 150th free webinar, and we are so glad you could join us to talk about 1D, 2D and 3D hydraulic modelling of bridges. TUFLOW will be the team presenting today, and it's their 23rd webinar, and we're so glad to be in partnership with them today and many more webinars to come. So Bill and Greg will be presenting, but there are so many here today, around 1,000 registrants and from over 60 countries. We're so glad you could join us. Let's get on to the presenters. Bill and Greg, lovely to have you with us today from TUFLOW, and also now Urs, Shuang and Chris. These 5, 2 present and 3 will be panelists who will talk to your questions and give answers and comments throughout the whole presentation. So, hey, one sentence. Go from the top. What do you think, Bill? One sentence about yourself.
One sentence, okay. Very hard. Yeah, no, just great to be here again. I'm really enjoying these webinars, and most people probably have known or heard of me, so I won't say any more.
Yeah, right now, Greg.
Oh yeah, look, I absolutely love partaking in these knowledge sharing exercises, and it's a great privilege to be able to spread some of TUFLOW's knowledge around the world. And yeah, excellent to be here.
And Chris?
Likewise, I'm just very happy to be involved in these education sessions. I'll be moderating the Q&A, so please forward through your questions.
Yep, for sure. And Shuang?
Same for me. Yeah, absolutely my privilege to be here. And yeah, I'll be answering the questions in the background.
Shuang's middle name is Guru. That's what Bill says anyway. We'll see more of why that's true as we go through this. And Urs, yourself?
Yeah, hello, I'm Urs, and I'm happy to that Bill asked me to join that for our little kind of research project we did together. So I'm happy to answer some questions as well.
And fantastic to have the mix. You're from Queensland Department
Transport, Main Roads. Yep.
Transport and Main Roads. So that's really good to have this mix of minds. Is that the way to put it? Mix of minds. Anyway, meeting of the minds. We're going to look at a poll. Greg, what do you think about this poll? Yep.
Yeah. Look, it's definitely, we've got 2 winning horses in the sector that people are from. Very predominantly commercial and consulting sector, with government in there as well, and a few others scattered around. In terms of what modelling software do you use for bridges? Yeah, we've got a lot of HECRAS, we've got a lot of TUFLOW. In fact, if that was a photo finish, it would come down to the nose, I think. But there's examples of all the others in there as well. If you added up all the others, it would be similar to the 2 main ones. So yeah, that's good. And in do you feel confident in modelling bridges? We have plenty of yes, but we also have plenty of no.
That's a fact.
As well. So look, this is the webinar for you, because we will really do our best to impart a little bit more understanding on this complex subject.
Yep, thank you. Thanks for doing those questions, everybody. That's such a useful thing. Sorry, Bill, you were going to say.
I think we should ask that last question again at the end of the webinar.
Yeah, I wonder whether yeses and nos would go. That might not be the same. It might be very different. All right, we won't take any more time. Well, let's get straight into this. Bill, you're going to kick off and then hand across to Greg, I understand, and then Greg back to Bill, and then we'll go straight to the Q&A.
Okay, thank you, Trevor. Thanks, Australian Water School, yet again. So today, the topic we're discussing is basically hydraulic modelling of bridges, and we'll try and cover all the different forms, 1D, 2D, 3D. So the plan for today's session is a little bit of theory to start with. What contributes to the energy losses for a bridge, and how well do we understand them? Talk about different modelling approaches, so obviously 1D, 2D and 3D. And I dug out an old presentation from 2006, and I'm going to just show a few slides from that one, because it's probably the most interesting bridge investigation I've been involved with. Then I'm going to hand over to Greg, who will present this joint research between ourselves and Transport Main Roads Queensland. So Greg will go through that, which will take roughly about 20-25 minutes, and then I will finish off with a couple of conclusion slides. So let's get into it. First thing I'd like to say, this webinar is really a sequel to the one we gave last year on energy losses at structures, and you can watch that through that link at the top or go straight to the AWS website. So I'm repeating a couple of the slides, but you know, there's reasonable amount of content in there regarding piers and other things. So if you haven't seen that webinar, I suggest that you have a look. So modeling energy losses, what are they? What are we talking about? So basically, the water has obviously got energy to flow downhill, and it is dissipated as it moves along, primarily as heat. And that dissipation of that energy is due to two main things, and that is basically what we call bed resistance, and most people would use the Manning's equation. And that's basically the water rubbing against the waterway that it's flowing along. So that will dissipate energy as heat. The other thing that happens is when water actually doesn't like changing direction or slowing down. And whenever it does that, it actually loses its kinetic energy. So it tends to lose energy in that form. And, you know, basically bridges are probably your best example of that, along with some other structures. So here we have water flowing through a bridge. It's being contracted, and then it's very turbulent as it comes through due to the piers and other things, and then it's expanding. And so there's a lot of change in water speed and direction, and that generates these what we call form losses, and that comes from the term change to flow formation. Typically for a bridge, the actual contribution from bed resistance is very minor or negligible, so we don't tend to bother with that. So when we talk about energy losses as a form loss, we're talking about a loss of the kinetic energy. And so many of you would probably remember that total energy of the water is the water surface plus its kinetic energy, which is V squared on 2G. And it's important to really understand that we're talking about velocity squared here. So, it makes a big difference to how fast the water is moving. Not proportional to velocity, it's proportional to velocity squared. So if your water is moving at 4 meters per second, you have nearly a meter of water of energy to dispel. And so we talk about form loss coefficients or energy loss coefficients, and that's basically a proportion of that available kinetic energy that can be dissipated. And for bridge losses, it's all about losing kinetic energy. As I said earlier, bed resistance is negligible. And to try and visualize this, I use this little image I took on holiday once. And so you got water flowing towards a drop, a weir, and it's got these sort of obstructions in there. And so the water surface forms this shape right at the top of the weir crest. And what's happening there, but the actual energy of the water would be fairly constant. And what's happening is as the water slows down, its V squared on 2G reduces, it slows down, and therefore the water surface rises. So that's why you're seeing this higher water surface here, because the water speed has dropped right down. And then where the water speeds up, the velocity V squared increases and the water level drops down. So that's why you're seeing this sag here. So it's I find it quite interesting and fascinating as to how water behaves, but it's very important as modelers to really understand the kinetic energy component. So what are the different energy losses associated with a bridge? Well, there's obviously due to embankments. If you have embankments, it's not a clear spanning bridge. Water is going to contract, it's going to expand, you're going to have a change in flow formation. Piers on obstruction, and they effectively are doing the same thing. They're actually basically contracting the flow between the piers, and then it re-expands downstream. So the water doesn't like doing that. It'll lose energy in that process. Overtopping can be a bit of a challenging thing, but basically if the bridge becomes surcharged, it becomes overtopped. So what goes on there? You can see in that picture, there's quite a lot of energy being lost with that wave. And then the deck itself, well, has quite complicated energy losses associated with this. And I'm showing those things in that order because we'll talk through those. So we'll briefly talk about embankments, piers, and overtopping. And then Greg will present the recent research with the Main Roads Department on deck losses. So approaches to modelling bridge losses. How do we go about doing this? And for embankments, it's all about your contraction expansion. So it's that change in formation and what are the form losses associated with that. If you are modelling purely in 1D, you have to, as a modeler, specify those form losses, those energy loss coefficients for entrance and exit. The entrance loss is really associated with the water expanding downstream of the vena contracta. So that's what's happening here. This water is expanding in here, and that's it. That's really what the entrance loss coefficient is trying to cover. And then the exit loss coefficient is what's happening downstream here, is that water expands out and dissipates its energy, dissipates its kinetic energy. So fairly straightforward. Well, you specify your loss coefficients, but then you need to know what to put in. So that's often the big challenge. 2D solutions are different to 1D because of their nature, they're more complex solutions. They actually simulate energy loss associated with the water expanding, like in the image there. But what 2D is not going to do well is you will probably not have a fine enough resolution to pick up this vena contracta. And so you might not model the energy losses associated with that particularly well. Also, 2D is 2D, it goes without saying, but there might be losses in the vertical. And so that's to do with water pushing up or pushing down, some vertical acceleration, and that will also generate losses. So 2D won't cover that. So yeah, you just have to be aware of that. One thing from a 1D perspective that's important to understand, I've taken this slide from the earlier webinar. It's quite important that the entrance and exit losses are being adjusted. And the reason for that is when the water level is below this bridge, so this bridge has abutments that go to here, but it's basically just clear spanning a trapezoidal channel. And for flow below that line, there's no change in velocity through the structure, and therefore there are no losses. So you have to bring your entrance and exit losses down to zero. Otherwise, you'll be falsely generating losses at that structure. But as the water level rises, the water starts to contract because of the abutments, and therefore we get a higher velocity through the structure than the approach or the departure velocities. And you'll probably start seeing some eddies forming on the outside. Now, 1D doesn't model those eddies. It's just modeling this as a unidirectional transition. So that change in velocity is going to cause losses. And so you need to be adjusting those entrance and exit losses according to those approach and departure velocities. And there's various formulas to do that. Another interesting, challenging one is actually when you do a 2D, 1D, 2D bridge. And it's commonly used. So you have a 2D domain, upstream and downstream, and you just want to, you've got road embankment, and you just want to insert a 1D bridge. What you have to be careful of is that the 2D is actually probably modeling the expansion losses possibly quite well if your resolution is fine enough. And so you may find that you just can't put in your standard 1D, 2D, 2D, 1D, 1D entrance exit losses. You have to adjust those losses to take that into account. Pier losses. So how do we treat pier losses? They're a little bit more straightforward for your standard sort of pier. It's not that this is a standard pier, but this is a nice image because you can see there's quite a, this is quite an obstruction. You can see there's a drop in water level on the downstream side. So you go from upstream energy here, which is the top of the bow wave effectively, down to the downstream energy down here where the water is fairly still. And so typically what we do in 1D world, we apply a form loss, a pier loss, often extracted from the hydraulics of bridge waterways, the KP value. And that's pretty easy for 1D. For 2D, we can do the same thing, but then there's a big question mark over how do you apply that 1D KP value. Is it across the whole waterway? Because it's coming from a 1D sort of solution. Or do we factor it up by the waterway cell ratio? And so in the earlier webinar that I mentioned, there's a number of slides discussing that. So if you want to explore that further, please do. But for very fine, another approach is just to make a very fine 2D mesh. How would that, basically what you're trying to do is to resolve the flow patterns around, particularly downstream of the pier. And if in the earlier webinar, which I mentioned, is again on the screen, flexible mesh at fine enough resolution and fixed grids that are using subgrid sampling, so you don't get that sort of distorted flow pattern around the pier, can both do a pretty nice job of reproducing the pier loss or the head drop. What is pretty important, though, you need a nice subgrid turbulent solution that's compatible with the cell size being much less than the depth. But have a look at that other webinar and you'll see some more information and some benchmarking around that. Embankment and deck overtopping, typically that's just carried out by treating the flow over the top as either upstream or downstream controlled weir flow. Typically with bridges, when the flow just starts going over the embankment or possibly over the bridge deck, it's effectively upstream controlled. And then as the water level downstream rises, it will start to drown out the weir flow. And you basically, through that transition, you revert back to the normal flow equations. So a fairly standard application by most software to model that. The other approaches, and these are of course becoming increasingly being used, is basically either a 3D shallow water equation approach. There's a few 3D ones. The first one I've got here is a 3D shallow water equation. So this is like a layered 2D shallow water equation solver. The nice thing with these ones is that you do have some representation of the transfer of momentum in the vertical. So it'll pick up those what we call secondary effects or the vertical effects in terms of how the any losses due to those effects. They're not the full Navier-Stokes equation, so they're still the shallow water equations effectively, which the 2D solvers use. But they're a step up by getting that vertical in there. So the assumptions in this type of model is that the vertical acceleration is assumed negligible. So basically, you can have the velocity transition up or down, but you don't have. You assume that the vertical acceleration is small, and that you assume a hydrostatic assumption. Like the 2D solution, if you're not resolving the flow patterns well, if your mesh is too coarse to do that, or you don't have a good turbulence scheme, you may need to revert to how the more simple way of just applying a form loss or drag coefficient to the actual obstruction, such as the pier or so forth. CFD, so these software basically solve what we call the full Navier-Stokes fluid equations, and they're pretty full on. I will not pretend to even really understand what people like Greg have done, and I know Urs is into this space. So it's really basically the Rolls-Royce solution in terms of the solution of the physical equations. It involves having very high resolution meshes, so you pick up all the fine detail in your structure, such as the piers, the rails, the bridge deck in detail. The concept is you're not having to specify loss coefficients. Basically it'll just come out of the solution. And the downside is that they have very, very long simulation times. So they're not really practical for your typical flood model, but they can be very useful for near field studies trying to understand the hydraulics of particularly a non-standard structure. So if you've got a bridge structure which is just not normal, CFD could be a good option. And finally, I'll mention physical modeling. So physical modeling, probably it was the mainstay, but rarely used for this type of thing in the past, but it can play a role. So that's another option to people to actually do physical modeling. And in that regard, I'm just going to now just talk through a few slides from a presentation I actually gave to the ASFPM conference in the States, that's the Association for Floodplain Managers, back in 2006. So it seems like a long time ago, but it's a very, very pivotal study, and I haven't personally been involved in a better study in terms of bridge modelling. That's actually a photo provided by one of the local landowners. That was 1952 flood, and that was his dad's ute. And it's come off the causeway. So back then there was a causeway that flows underneath all that, and that was the main crossing. That was how you cross this river section or creek section. But that causeway actually plays quite an influential role in what happens. Where is Eudlo Creek? Well, it's here, this part of Australia. For those who know Australia or Brisbane, you may have heard of it. It's when you drive to the north coast, you'll cross over it. And that's really all it was. It was just a road over a small creek until the February 1992 flood. And they had just recently, within a couple of years beforehand, upgraded the single carriage highway to a dual carriage highway. They replaced some culverts and they rearranged things at the crossing. Anyway, Queensland Main Roads Department ended up in legal proceedings with the upstream landowner. They basically had a favourable outcome to those legal proceedings, and then the landowner wasn't happy, and he took it all the way, in the end, to the High Court of Australia, where all 7 judges heard the case. And they decided that, yes, there is a case. They upheld the appeal, and they asked for the case to be reheard. In 1998, Main Roads expected that appeal to be upheld, and so they commissioned pretty full-on investigations to establish the pros and cons of this emerging 2D modelling for flood modelling. And they also wanted to get a much clearer picture of the impacts of this road crossing. And that study then fed into the rehearing of the case in 2002. What's particularly nice, I won't go into all the details, but what's particularly nice about this study is it allowed a pretty exhaustive comparison of models. So there are 8 different models in the mid-1990s, so the initial hearing. There's Rubicon and Mike 11, late 1990s, Estuary, which is the 1D part of TUFLOW. TUFLOW in 2D form, FESWIMS is a 2D flexible mesh model out of the States at the time, and a physical scale model. They actually built a 1:30 scale model. Then during the court hearing, they added Mike 21, and then RMA2 was also used. So we have this quite amazing suite of comparisons that can be made. So I'm just going to summarize those in a nutshell in terms of what's of interest today. And basically, without calibration data at the bridge, the 1D models, and there's 1, 2, 3 of them there, all struggled using standard loss coefficients at the bridge. They needed exceptionally high loss coefficients to calibrate to, and there is good recorded data from 3 floods. One of the floods occurred during the study. Interestingly enough, the 2D models performed pretty well, and the calibration data helped fine-tune those. And the physical model also performed quite well in terms of calibration, but calibration data was essential, but it really did struggle prior to not being calibrated. So that was really interesting, and for me, it was quite, in hindsight, I've often thought about this, but why did the 1D model struggle so much? It was early days of 2D, but why did the 1D model struggle so much? And it really comes down to, this is a road crossing through here. This is a photo when they had the single carriageway, and they also used to have some culverts here, and the bridge is actually sitting in here. And the flow is going from the bottom of the screen through, and it hits this very dense vegetation downstream of the road. And what happens is, so you can see this, like this embankment around here. You can see that's this embankment around here. And you can see the flow. This is the case post-duplication, where they got rid of the culverts up here and they've got the bridge structure here. And this is the 1992 flood event shown. And so the water contracts pretty viciously. And I was there after the 99 flood, and it basically it hits this wall of vegetation. In fact, there's the causeway. The vegetation just gets lifted off the causeway and is put vertical like a carpet. And the water is forced to northwards here along the causeway very, very harshly. So you've got a very tight bend there. Normally after a bridge crossing, the water would just continue on in a fairly uninterrupted manner. But in this case, it hits this wall of vegetation and it is forced to flow very strongly to the north. You can see the water level contours here. So that's 0.2 meter increments. So you've got 1 meter drop from here to here. Yeah, and you've got a very, very sudden drop in water level. So the 1D models just totally struggled with this because they were not picking up this energy loss that's happening in this space here as the water is forced to expand, basically like a right angle bend. So the only way they could model the energy loss was to put in a very, very high exit loss on the bridge, which it's probably not, they weren't that comfortable doing. 2D went pretty well because it picks up those flow patterns. But as for the physical model, that was interesting. So when they first ran the physical model, watered through it, it was terribly low. It didn't come close to the recorded levels in the 83, 92, and 99. And then they went out and surveyed all the trees, and actually all these pieces of dowel actually represent each tree that was picked up, and they're of different size and dimensions to reflect the size of the trees. And even that the physical model was still under-predicting the flood levels. And so it wasn't until they stuck all these pieces of rock in that they actually got a good calibration. And once they had the model in that space, it's actually quite a useful model. You can see here, this is a dual carriageway scenario. But what I'm not a physical modeler, but what was really interesting to me was basically, well, back then, no one believed a computer model except for the modelers. There's too much faith by modelers who generated results on computers, and no one trusted computers. But the big challenge for this physical modeling was that everyone believed it because they had to be right. You can touch it, you can feel it, you can walk around it, you can see the water flowing. But without all those changes, without calibration, that physical model was horribly wrong. So quite a fascinating exercise. So on that note, I'm going to now hand over to Greg to continue with the joint research we've been doing with Transport and Main Roads Department.
Okay, good afternoon, everyone. Okay, so this is, I'm going to present a section now where TUFLOW has partnered with the Queensland Department of Transport and Main Roads to look at the issue of, trying to improve the form loss coefficient models that go into 2D models that include bridges. So here's a short section of video. So I usually say to people, what is the real issue here? Kind of at the very outset of this, you'd look at that and say, well, that river probably used to work just fine until we put a bridge across it. So, what humans have done with civil engineering, putting bridges across rivers, just really doesn't help with regard to how well rivers work. But it's, we can't, the option of not putting the bridge there is not an option. We have to have a bridge. So, understanding how that bridge then impacts the flow and gives us a change in water levels. You can even see in this image that the upstream water level is higher than the downstream. So if you own a house that's in some proximity to that upstream water level there, you'd be very interested in these results because you want to know whether or not the water is now going to come across your floor level of your house. Secondly, and perhaps more importantly, the real issue here is that the flow around a bridge is very three-dimensional, and the physics of that are just not captured very well by a 2D solver. You need to implement a submodel within that 2D solver that captures the losses associated with all of the 3D flow patterns near the bridge. But what Queensland Department of Transport and Main Roads have recognised, and probably everyone in the industry knows, is that different software have got different submodels. In many situations, there's very little published guidance on what the input parameters should be for those submodels. What that effectively means is that when people build a flood model and they choose a software package and they set up their submodel for the bridge, it's very easy to get it wrong. And unless you've got some industry experience behind you or some calibration data, you can end up with a model that's terribly wrong and just not realize it. So to try and improve the quality and standard of work in this area, both TUFLOW and Queensland Transport and Main Roads wanted to be able to publish a recommended approach with parameter guidance so that, mistakes happen less often than they were happening before. So to start us on our journey, Urs, who is one of the panelists on today's session, set up some beautiful 2D models here using the Flow 3D CFD software. And we ran 2D models mainly because you can get them through reasonably quickly with CFD. As we've mentioned before, CFD is notoriously computer intensive, and to run big 3D models can take a lot of time. So just by running some simple 2D models is often a good way to kick some research off. This picture here is of a two-dimensional vertical slice through a very standard Australian bridge design, which is a flat deck with curbs and guardrails. We recognise that people in England will be a lot more familiar with arched bridges, and many of the big highway bridges also have got T-girder or large I-beam structures underneath the deck that make it a bit different to this as well. But this is a simplified version, and it's very common in Australia. Now, this slice is coloured according to flow velocity, which is going from left to right. So you can see a vena contractor underneath the bridge deck where the flow is accelerating. And you can see a wake. I'll just bring up my laser pointer. So yeah, the flow acceleration is in this region under here underneath the bridge deck. And then downstream of the bridge here, we've got a wake. Other features, you can see we've got surface waves happening on the surface. We've got a height difference between the upstream water level and the downstream water level. And so it's showing everything that we think it should show. Now, I'm going to point out some standard, our adopted nomenclature on this, which is going to feature in a lot of the graphs I'm going to show you further on. So I'll just try and point this out to make it clear. So HB is the height to bed. It's the height underneath the bridge from the soffit of the bridge deck down to the creek bed. So that's HB. T is the thickness of the bridge deck from the soffit up to the top of the curve. And further on in the study, I'm going to talk about the ratio of HB on T, because that turns out to be quite important, whether you've got a thin bridge up high or if you've got a thick bridge down low, the ratio of HB on T is quite critical. The other one two parameters I'm going to point out is tailwater, which is the height of the downstream water level above the soffit of the bridge. So that's on the downstream side, tailwater. It's not down to the creek bed. It's just from the soffit of the bridge up to the water level. And then what you can see here, I've also shown the head loss between upstream and downstream. So Urs ran a whole lot of these 2D CFD models. He ran them for different bridge thicknesses, 900, 1200, 1500 bridge thickness, and also for different velocities, 2 meters per second and 3 meters per second. The plot that we're showing here is the energy loss from upstream to downstream of the bridge expressed in meters, the height loss, and that's showing as a function of the tailwater value. So reasonably, when tailwater is zero, this is a 2D model, so it's got no piers. Reasonably, you would expect that when the tailwater is zero, that when the water sits underneath the soffit of the deck, that there would be no associated energy loss with the bridge. Once the water gets above the soffit, the energy loss increases quite rapidly until it reaches a peak And then once the bridge is really, really overtopped and drowned out, then the energy loss actually falls again after that. What you can see here is that the dashed lines for 3 meters per second are bigger energy loss than for 2 meters per second. And the other thing you can see is that the tailwater at which the peak loss occurs seems to shift to the right for the grey curves, which is a thick bridge deck. So when the bridge deck is really thick, then the energy loss is peaking at a higher tailwater level than for a thin bridge deck. What you can also see from this plot is that in general, the curves have a similar shape. Apart from, being stretched differently vertically and horizontally, they all have a similar shape. So this begs the question, can we find a way to non-dimensionalize the results that collapses all the curves together? And of course, I've loaded that question. Of course we can. This is what happens now to all of those curves. If we normalize in the vertical direction, we compare the energy loss or the upstream downstream height difference, and we compare that to the theoretical velocity head of the flow. On the horizontal axis, I'm now renormalizing tailwater with respect to the bridge thickness T. You can see now that those family of curves have all collapsed pretty much into one curve. That is a very useful curve to have because we can use this later on to generate a parameterized loss model. So what we can see here is that the peak is occurring for a tailwater level that's around about 1.6, maybe 1.8 times the bridge deck thickness. And the other feature of it is that in general, all of these peaks here are around about a head loss coefficient, somewhere between 0.25 and 0.3. I've kind of eyeballed that and said that looks like about 0.28. Now, all of these cases presented here are for the situation where the under deck height to bed was 4 times the bridge thickness T. It turns out when you rerun all the models using a ratio of 2, so this is making the bridge sit lower down to the creek bed, then the peak loss coefficient actually climbs up to about 0.42. And if you set the bridge up a bit higher, so the underdeck height is about 6 times the thickness, then the peak form loss coefficient drops down to about 0.2. Interestingly, the value of 1.6 here, the ratio between tailwater over T at which the peak loss occurs, so this position vertically here, that doesn't seem to be very sensitive to that ratio of HB on T. It seems to occur at the same point. So we've got this beautiful simplified 2D CFD modeling, but the next question we have to ask ourselves is, well, how accurate is this compared to a real world model? Most people these days have faith in computer CFD modeling, provided that you've selected appropriate turbulence models, mesh size, and the work's been done by someone with some experience and it's peer reviewed, then you can have some faith in CFD modeling results. But when it comes to flood modeling, this is critical. People's lives can be at risk with flood modeling. So it'd be really good to actually have some real world data to compare this against. Here is one of those bridges, simple deck and rail bridge with relatively minimal embankments either side. This bridge is fairly low immunity. It's quite low down to the creek and it floods quite often. Historically, it looks like it goes under on average once a year. And it looks like it's really low down compared to the creek bed, but what this plot doesn't show is, what this photograph doesn't show is this water under the bridge is actually really deep. That water under there is already like 2 meters deep. There's quite a height available down to the creek bed underneath that bridge. In order to get actual measurements of this bridge, upstream and downstream water level sensors were installed in about 2021. And we've got to thank the Moreton Bay Regional Council for installing those sensors and maintaining them and calibrating them and making all the data available for us. So yeah, our thanks goes to them. And very fortunately, in February this year, we got an absolutely fantastic flood event. This is a plot of the upstream and downstream water level either side of the bridge over a period of about 3 days towards the end of February. You can see that the water was over the bridge for most of that 3 days. It was a phenomenal flood event. In fact, in the upstream reaches of the catchment, it's a small catchment that feeds this creek, but there was nearly a metre of rain, nearly 40 inches of rain occurring in 24 hours in the upstream reaches of the catchment. So it really, the water was just coming down, just absolutely coming down. We managed to get out to the bridge. There's a few gaps in the data here, but we managed to get out to the bridge approximately at this point here. And it's from a distance, we're able to take some video footage of the water going over the bridge in this region here. So I'm just going to step you through that. So we didn't arrive right at the peak of the flood. We arrived an hour afterwards or so, but that water level there is still more than 2 meters above the bridge deck. It's almost hard to believe there's a bridge in there except for a small dip in the water surface level. If we step forward a little bit in time, you can see a bit more formation now. This is basically, that's the road on the other side. You can just see going up on the other side there, and we've got a guardrail on this side. Stepping forward a bit further in time, this is our flood marker now, so you can see the water's now 1.4 above the bridge deck. And also you can see there's a bit of debris build up on one of the guardrails. One more with the water even lower now, down to 1.2 meters. So this is at kind of close to the level at which we've actually got the peak afflux of the bridge, the biggest energy loss between upstream and downstream. We wanted to get a picture of how much debris was on the guardrails, so we went back a couple of days later after the flood event, but unfortunately the local residents had already cleaned our bridge off. So you can see the evidence of all the vegetation damage and scouring, but the debris on the bridge was gone. So we don't actually really know to what extent the guardrails were blocked by debris. So we've got this beautiful data now from these gauges, upstream and downstream. How good is the gauge data? I started before by saying how good was the 2D CFD model, so let's get some gauge data. Now, of course, you have to ask the question, well, how good is the gauge data? So we're going to complete the picture by considering the 2D CFD modeling, plus the real world gauge data measurements, plus some 3D CFD modeling, and we're going to see if we can tie it all together into a set of results that are consistent. So in order to check the gauge data, we also ran 3D CFD model of the bridge and surrounds using Flow 3D and also open foam software. I don't really have time to go into detail in the software setup. What I'm plotting now is the head loss across the bridge as a function of the downstream water level on the x-axis. And so the bridge soffit is at 76 meters. So we've put the image of the bridge on this graph and rotated it around 90 degrees so that the soffit lines up with 76 meters and it's approximately scaled by height in the x-axis direction. All of the gray dots represent the measured gauge data for upstream, downstream water level differences. And the orange curve is what came out of open foam CFD models. The blue line is what came out of Flow 3D CFD models. Unfortunately, we didn't run the open foam CFD models to high enough flow rates to get the extra dots. We were out of time and then other priorities took over after that. So, but we've got the data there. What's very interesting here is that you can see that the gray dots, if you kind of draw a mean line through them, the gray dots are showing something of a very similar shape to what I presented before for that generic curve for the 2D model, the 2D CFD model, and the 3D CFD results in general are agreeing both in shape and in magnitude. It's not an absolutely perfect fit, but I'd be more suspicious if it was a perfect fit. But I think, the magnitude of these results is looking around about right. So I reckon the gauge data is reliable. It's fact. I think we can use it to check everything that we're doing here. So the next step was to actually implement that generic loss curve that I presented before into a 2D solver. And of course, you know, being TUFLOW, we integrated that into TUFLOW HPC solver. I'm not going to try and explain the details of this equation over here, but in general, the concept is that you have one loss coefficient for up to the deck soffit. But for this bridge, because there are no piers, this pier loss coefficient K1 is 0. Then we linearly transition between the pier loss coefficient up to a peak loss coefficient at a height of water level, which is H2. And that H2 is H1 plus 1.6 times the total solidity of the deck and guardrails put together. So that 1.6 is this F expansion here that goes in here. And that's a customizable parameter you can put into the model. K1 and K2 are customizable parameters. And then beyond H2, then we get a reciprocal decay of the loss coefficient beyond that. It's a fairly simple model. So this is what happens now when we put that model into TUFLOW HPC and run 2D models of the flow over the bridge and the surrounding areas. What you can see there again is that we've got a pretty good comparison now between what's coming out of the 2D solver and the actual measured losses for the bridge. The dotted lines are total energy. The solid lines are the difference in water actual surface elevation upstream and downstream. What's interesting is that we've got approximately the right maximum peak. We're getting about the right shape. Once you get to really high water levels over the bridge, quite an interesting effect is happening with the surface waves over the bridge. And the 2D shallow water equations, I think, are not quite getting the surface wave shape absolutely accurate. And that's because they use depth average flow. But as I talked about before, you know, this is a very, very 3D problem of the water over the bridge. So although the surface wave shape might not be exactly as per the real world model, what's interesting is the actual energy losses are right. So the 2D solver is doing the right thing with energy, and that's really what counts. It's also showing that we've run it for a form loss coefficient of 0.28 and one of 0.5. The 0.28 seems to be giving the better result fit through the grey dots. And that's in line with the results we had from the 2D CFD modeling and this particular geometry aspect ratio of the bridge in terms of the HB on T ratio. The results can depend a little bit on transverse velocity profile, which is in turn dependent on your choice of eddy viscosity model. So there is some sensitivity to that. But in general, as I said, the peak form loss coefficient of 0.28 pretty much agrees with the measured data. And the negative afflux at higher water levels, most likely surface wave features of the 2D solver, whereas the total energy gives you the right result. Another way of looking at the energy losses is to actually go back to 3D modeling. But another option, instead of doing CFD modeling, which we mentioned was computationally very expensive, is to actually use a 3D shallow water equation solver, uses the hydrostatic pressure assumption, such as TUFLOW FE. So it is a 3D solver. It uses a split mode solver for the 2D surface wave component versus the 3D actual detailed flow vectors. It can also use a sigma mesh, so the mesh stretches up and down. So this means that this solver is particularly well suited to running large domains of rivers or estuaries and solving them in a computationally efficient way, much, much better than CFD can do in terms of the size of the model that you can run. And something we've incorporated into this solver now is the ability to have a real physical structure shadow cells and apply a form loss or a drag coefficient to those cells. So you can see that in this little plot on the right here. This is the blue bar in here is the cells that have been shadowed by the bridge deck and have a form loss applied. So I'm just going to show you a couple more detailed images out of that. The first one is when the water level is first reaching the deck, and you can see it's only the top layer of cells that are getting shadowed and have a reduced velocity. And you can see the velocity vectors underneath here through this curtain plot. They dive under the deck and pop up again. And you can see in this plot here also the degree to which the bridge is over a scour hole that's been presumably created by the presence of the bridge. At slightly higher flow here, the water level's well above the bridge deck now. So the mesh has been stretched upwards following the water level. But again, the structure is shadowing out these cells here. So the next question is, of course, well, how well does this do against the measured data? And this is the result here. If you just simply use a drag coefficient of 1.0, the blue line is for a drag coefficient of 1.0 for the shadowed cells, which is pretty much an industry accepted drag coefficient for a bluff body of some description. And it's giving a pretty good result there. So look, TUFLOW FE is also a viable way of establishing efflux levels for detailed bridge designs. So as a quick summary of this block of research, we've got 2D CFD models, we've got measured gauge data from a real bridge, we've got 3D CFD models, plus also the TUFLOW FE modeling, and it is producing a very remarkably consistent picture, particularly a very strong generic curve shape for the form loss coefficient as a function of water level. Also, the peak loss is occurring not when the water first gets to the top of the bridge deck, but actually fairly well above the top of the bridge deck as well. And that's even without guardrails. It still happens that the peak loss occurs when the bridge is still somewhat inundated. Importantly, Queensland Department of Transport and Main Roads is planning on recommending the adoption of this model and associated parameter guidance. It's not out in the public domain yet, but it will be soon. So that's something you could ask us about afterwards if you wanted. Some of you might be thinking about how does pressure flow fit into all of this? Pressure flow is when the surface upstream and downstream of a structure is broken. It's disconnected by the structure. So the structure is in the way between the surface upstream and downstream. I think really the real question that you should be asking is the flow upstream controlled or downstream controlled? If the flow is downstream controlled, which is what I'm showing here, this is out of federal highways guidance. This is for pressure flow case 2. This is a downstream controlled scenario. You can see here in the equations, they have a loss coefficient times an energy head. And they particularly explain that as the loss coefficient KB is an energy loss coefficient which varies with bridge inundation. That's exactly what I've just described to you and what we've implemented. This is a perfectly correct way of approaching flow that you might previously have thought of this as, well, this is pressure flow. But the truth is, in this situation, when it's downstream controlled, pressure flow is not a special case. You can still represent the energy loss as a loss coefficient times the energy head of the flow that's going through the structure. The situation where it does become different is when the flow is upstream controlled. In other words, in this diagram on the right, this is pressure flow for case 1. If this flow downstream of the bridge has gone supercritical, then the energy loss from upstream to downstream is no longer a function of the flow rate. They're not connected anymore. Flow rate is independent of the difference in water level between upstream and downstream. What that means is you can't model energy loss as a function of flow rate. There's a complete disconnection there. So that has to be treated differently, usually by putting in a 1D element that allows for supercritical flow calculations. This situation can also occur if you've got culverts under an embankment with or without a median drain, in particular where you've got steep ground and the flow accelerates and becomes supercritical very quickly. So that's, as I said, this is a different case. Further research that we've got in mind, we want to extend the range of HB on T to less than 2 and more than 6 to see how the parameters vary at different ratios. The effect of the width of the bridge. We've done one quick study on that, and we found that it wasn't a strong effect, whether the bridge was a really wide one or not. But there will be some sensitivity there that needs to be looked at. Having parallel bridges together, dual carriageway, where one bridge shields the other bridge, that needs to be considered as well. And another thing is the underdeck geometry. The bridge we've shown there has got a smooth underdeck. Some of the big highway bridges will have much more structural and complicated underdeck design involving beams and girders. So we need to look into that in a bit more detail. So yeah, watch the space. Okay, Bill, look, my voice is about to give out. If I can hand that back over to you, and then we'll move on to question and answers at the end. Thank you for your time.
So the conclusion from today's webinars are effectively when you're modeling bridges, it's important to understand that these are energy losses, kinetic energy losses primarily. They're not bed-resistant losses. And it's all caused by the flow being forced to contract, and then it's being expanded, it slows down and changes direction due to things like embankments, piers, bridge decks, and of course overtopping. So that's what's fundamentally driving the energy loss around the bridge structure. If you're doing it purely in 1D, you'll be specifying some loss coefficients. What's important to understand is that those loss coefficients need to be adjusted with height depending on the flow condition. And so that's normally based on 1D approach and departure velocities. And our approach to that is that that's all automated. So it adjusts those losses automatically for you. If you're embedding your 1D bridge inside a 2D domain, just be aware that the 2D is probably covering some, if not all of your, or most of your exit losses. So you can't simply apply the full losses to a 1D bridge embedded inside a 2D model. We have, and Schwaling is giving a paper at the upcoming HIWE H3RS conference on techniques for where we automatically make those adjustments based on the 2D approach and departure velocities. That's a very nice new feature. If you're using 2D, it's important to understand it's contracting and expanding the flow, and therefore it's actually generating and modeling most of those losses for you. But if you've got fine scale flow formations, it's unlikely that your mesh will be fine enough to resolve those. And there may also be losses in the vertical. So 2D may look fantastic, but it's not necessarily, it certainly will not be the whole story. So you may need to apply some additional form losses. You'll certainly need to do it for piers. It's very rare that your mesh is fine enough to resolve the pier losses. So normally there are these additional losses that are fed in, and that's sort of where Greg was coming through on the bridge deck. What this recent research has certainly done is greatly reduce the uncertainty, in our view and TMR's view, of how you approach modelling the losses associated with a bridge deck. As I mentioned, it is important to have a good subgrid turbulence model that's depth cell size independent and is not affected by the depth, as in cell size being a lot less than the depth. The recent TUFLOW versions, both FV and HPC, have adopted that new turbulence approach. We're seeing an increasing, CFD has always been a good option for specialized bridges, and increasingly so, because as computers get faster, you can deal with the long run times much better. But we're also seeing some really positive results by adapting TUFLOW FV, our 3D flexible mesh solver, adapting it to be able to model blockages in the horizontal, such as bridge decks, and applying some additional form losses in addition to that. The TMR TUFLOW investigation, look, that's been a really fantastic exercise between the two parties. And in a way, we were actually hoping to present all this a year or two ago, but due to COVID and other things, we were sort of sidelined and it didn't happen. And that's right, the TMR Tech Forum was cancelled twice because of COVID. And in that time, we had this fantastic data set come through from the floods last summer. And so, as Greg was showing you, it's just so nice to have such good calibration data to verify all this modelling, because no modelling is perfect, and we really need to have that quality data. So that's been a nice outcome of COVID, if you like. But there's always need for ongoing research. So as Greg talked about, different bridge designs and configurations. How do you deal with dual bridges and so forth? So we're hoping that we may be opportunities to continue this type of research to further inform bridge deck losses. So that's all from me. So thank you for attending, and I'll hand it back over to Trevor.
Yep, thanks very much. What a fantastic explanation, more than an explanation. It's been really good to hear all that examples and data. Chris, you're going to moderate this Q&A. We're at 1 hour, 5 minutes, 6 minutes, but it's just such a interesting topic, and people are highly interested. Why don't we just go for 5 or 10 minutes? What do you think?
Sounds good. Sounds good. There's been some great questions, and even though Schwan and myself have answered them, I think there'd be great value in just letting Bill and Greg just talk about these various questions and hear their thoughts. All right, so let's start. Question number 1. Bill and Greg, what would you do if you didn't have any pier layout or bridge deck information? What conservative assumptions would you make in your modelling under that scenario? How would you approach modelling if you didn't actually have any bridge details? Would you put numbers in there? Would you not put anything in there?
Oh, that's very tough, because bridges vary so much. And Urs may be a good one to comment on this. I do know that some main roads departments like to target a certain velocity, a maximum velocity through bridges. So the size of the constriction is obviously sometimes driven by not exceeding, say, 1.5 meters per second. Otherwise, scour and things like that might become a problem. So if you don't have any information on a bridge, you may be able to, through some desktop calculations, estimate the size of the opening that might be there. Urs, any comment on that?
Yeah, no, I will agree. Instead of just assuming some formulas, I would try to actually assume what the bridge would look like, and then go to the guidelines or what information you have, what you would assign to a typical bridge if that was the bridge. And if you want to be conservative, then you probably assume like quite a thick deck and maybe short spans with relatively thick piers. That's probably my approach to that.
Yeah, I'd agree. Yeah, being conservative would be a good. Think of solid bridge and thick piers.
Along the same line of thinking, is there some sort of baseline FLC value that you would recommend for adopting for the bridge deck and guardrails without any meaningful calibration data?
Oh. Yeah, so modern no bridge, I'd just be adopting the values that Greg was showing, using that method with the inflection point roughly 60% above the deck.
Yeah, I think so. You can probably have a reasonable guess as to what the HB on T ratio might be. Otherwise, you would just use you could probably just use a center value of 4, like it is in the table in our presentation there, with an associated loss coefficient of 0.28. And that would be in addition to any pier losses that might be in the model. Yeah, and I think that would be, of course, you'd want to caveat that in your results when you write up your details of the modelling effort, but I think that would be reasonably defensible.
Yeah, and I would just probably add, you have to be a bit careful, because when you have a large bridge that covers the banks as well, because your ratio with HB to T will be varying. So you might want to maybe break up your bridge where you have a deeper section or where you have shallower sections. So that's probably something to be aware of as well. So you can't probably apply one value for the whole of the bridge.
Yeah.
That actually provides a nice lead into 2 other questions. First, we'll just talk about maximum K value. So you mentioned a value of 0.3. That's a lot smaller than the 1.56 bridge submergence factor for TUFLOW 1D B and BB bridges and also the hydraulics of bridge waterways. Do you have any commentary on that?
What people don't, and we've got a wiki page, if people email support, they'll direct you to it, or we'll put it in the answers. That 1.56 is only for pressure flow. It is derived from the point, I think it's 1 on 0.8 squared or something like that. Can't quite remember exactly, but it's derived from the pressure flow contraction of 0.8 that's in the hydraulics and bridge waterways. So it's like orifice flow. So there's nothing to do with submerged bridge flow. So there's this misunderstanding. People just see the 1.56 and look, in the old 1D models, we used to just automatically go to 1.56 for that reason. But yeah, no, you've got to be very careful using that 1.56. And we do have a nice description of all that on our wiki somewhere, which we can put in the formal responses or just email support@tuflow.com.
A question, and this is very much a TUFLOW specific question about the implementation of your form loss inputs. When you look at the layered flow constriction input, there's two primary parameters. There's a blockage parameter, and there's also a form loss coefficient parameter. Should you be inputting data for both, or just inputting data for your form loss coefficient? Do you have any clarifications on that front?
Well, the blockage, by putting a blockage in, what that means is that you'll get a closer representation of the velocity through the bridge, because the flow area is reduced. And so if your K values are based on the velocity through the bridge, then you should put the blockage in. If the K values are based on the approach velocity, which I think probably some of the hydraulics and bridge waterways ones are, it is probably the case you don't put the blockage in, say for your piers. And it looks, it's a tricky space, but it's important to understand what, the actual K value is applied to the velocity through the structure or at the right upstream face of the structure. So you need to sort of understand, where those K values should verify from.
Yeah, can I just add to that, Bill? The K values, the loss coefficients that we presented there were based on the structure velocity, which is the velocity through the structure. So it is working on the principle that the blockage factors are applied. Yeah,
and that sort of suits, because what we feed into our TUFLOW or whatever will be that, it'll be like for like. So that's really important.
Yeah, I mean, I can just add something to that as well. When we did a study like a few years back when we looked at piers, and we found if you just apply the bridges and waterways factors and applied a blockage as well, so you were slightly conservative.
Yeah.
So if you wanted to match the bridges and waterway ones, you would need to not put any blockage in. But as you said, the velocity distribution is slightly off then through the bridge.
Yeah.
And therefore we recommend maybe if it's really important, maybe you go one curve to the right or something if you want to put on it. And I think there's going to be a paper as well on the conference on that, okay, on the HWRS conference soon.
Oh, excellent. And and you can always adjust the K value by the ratio of the two flow areas, the upstream and and just be careful using the upstream one. It's not necessarily the whole waterway. It's basically what we call the effective area. So yeah, anyway, we won't get into too much more complications now, but yeah.
You must be reading my notes, Bill, because the next question is, could you discuss how to handle the ineffective flow areas upstream and downstream of the bridge, specifically when the bridge opens for 1D and 2D?
Yeah, I could talk about this is another whole webinar. Sorry, Trevor. But look, it's this is if you're doing 1D only modeling, really. So to get the right approach and departure velocities to the structure, and so the loss adjustments. This applies to culverts as well and other structures. It is important to be using what we call effective area. So that effective area is the total area, but it's reduced by the ratio. Like if you got Manning's End is twice as high on the bank as it is in the main channel. Your effective area for floodplain, the high Manning's End section will be reduced by 50%, and then the total area is reduced. So the effective area is typically always less than the total area, and then that is used to generate the velocity. So the effective area will always produce the mainstream velocity. The velocity that comes out is the mainstream velocity, and that's really important for approach departure velocity adjustment of structure losses. It's also really important if you're actually doing 1D AD modeling, the transport of a constituent down a 1D system. So if you don't have the right mainstream velocity, you will not get the right transport mechanism in your 1D model. Did that make sense? There's a section in the TUFLOW manual on that.
I have two more questions, Trevor, if that's okay.
And that's good. Keep it going. It sounds good.
On the line of, or on the same subject of 1D modelling, Bill, the question is, with increasing computational power and the view that 1D is struggling to actually represent the physics appropriately, why would a 1D solution ever be preferred over a 2D solution? Can you see a need for one, or they're both still valid?
I mean, these days, I think 2D is generally the preferred approach, and you do need to be using a good 2D solution. There's a lot of variation in the quality of 2D solvers. But there's always a place for 1D. You might have a broad scale, like the Brisbane River model is a monster of a 1D model, but it runs in a few minutes, and we could run it through Monte Carlo analysis. So that had very, very detailed calibration, including around bridges, and so for submerged bridges in particular upstream. So there's still a place for 1D models in like Monte Carlo analyses or flood forecasting, where you just have to have that very fast runtime. But over time, like in 5-10 years' time, I suspect it'll be very much all about 2D.
And look, I'll deviate from the 1D, 2D discussion for this last question that was asked right towards the end of the presentation. Can you discuss the key differences between upstream controlled and downstream controlled flows?
I'm going to pass that to Greg.
Yeah, okay. When the flow, if a flow goes supercritical, so the flow velocity is faster than its wave speed, then it's kind of like, supersonic. You can think of it like that. Downstream of that, you'll usually get a hydraulic jump where it transitions back to subcritical. In that situation, the downstream water level, if that changes, then it makes no difference to the upstream. The upstream water level doesn't care whether the downstream water level is at one level or a bit above or a bit below. In that situation, you call that upstream control. The flow rate is only a function of the upstream water level, and it's got nothing to do with what the tail water level is downstream. If the flow doesn't go supercritical, then it means that the downstream water level actually does determine what happens upstream, because there's wave communication from downstream back up to upstream. And so we call that downstream control. In reality, the flow rate is a function of both upstream and downstream, but at least it is in some way sensitive to what's happening downstream. So that's called downstream control. I hope that made sense.
Very clear. Thank you for explaining that. I think we'll leave it there. We've run well over time.
That sounds good, and a great moderating. Thanks, team, for doing that. And there's still more questions, obviously, on the Q&A. I think they will get answered, and you get everybody will get an email of that. As will everybody will get a link sent to them for the recording of this webinar. The live attendees will be emailed the certificate of attendance within the next 2 business days. And that'll go toward your CPD hours. A short 1-minute survey at the end will be really appreciated. If you can just take a minute, bang, a few tick questions, and we will have better and better webinars happening, because we'll hear from you guys. That'll be great. What's coming up is incredible. Well, just take the middle row. That's TUFLOW. Is that right, Bill? That's TUFLOW there, isn't it? It is.
Yeah.
4 webinars. One webinar still to go here. this year, and 3 more and many more coming up in 2023. I think that should be a very interesting year. Flood Modelling 101, don't miss that, 15th of February. The first row you can see there, on-demand, standalone and series courses, and the last row are live courses coming up. So get stuck into it, open the website, log on, be fantastic. People, team, TUFLOW team, what an A team. It's just unbelievable to have so much knowledge spread across so many years and so much experience. Thanks so much for taking the time, taking the effort, putting in the time and effort to Bill, Chris, Shuang, Urs, and Greg. Really appreciate your time. Any last thoughts?
No, we just love doing these webinars. A lot of preparation, but
we
always get fantastic feedback. So it's very rewarding.
Yep.
And you guys do a great job. Absolutely.
Thanks so much. We love doing it. And look at the thank you notes coming through on the chat line. That does a lot for us too. All right. We're going to wrap it up there. Thank you so much, everybody, for staying with us. And let me tell you, there's been a large number stayed with us right past the hour. Thank you very much for being with us. See you soon. Bye for now. Bye, everybody.
Thanks, Trevor. Thanks everyone.
Bye. Yep. Bye.
Thanks for watching. Subscribe by clicking the link below and click on the notification bell to stay up to date with new releases. For the latest in significant, innovative and critical advances in water science, technology and management, subscribe now. To build your skills, enhance your technical knowledge and learn from leading experts in water, visit theaustralianwaterschool.com.au and discover our online training courses, both live and on demand.